There are three different symmetries that we'll look at. One is x-axis symmetry. And for x-axis symmetry, we normally have equations that have y to an even power or the absolute value of y. There's a test to see if there's x-axis symmetry. You replace y with the opposite of y, and if you get the same equation, then it has x-axis symmetry. Here is an example. When we take this and fold it over the x-axis, we would get this line here, and because of that, it has x-axis symmetry. The second is y-axis symmetry, which is similar, except now instead of y being to an even power, x is to an even power, or x is the absolute value of x. And the test is that when we replace x with the opposite of x, we get the same equation. So here is an example. If we would fold this across the y-axis, this would fall right onto this one here, and that would be symmetric across the y-axis. The last one is origin symmetry, and there's two cases. You have x raised to an odd power, and at the same time, all the y's are raised to odd powers, or all the x's are raised to even powers, while all the y's are also raised to even powers. So if they both have the same powers throughout the entire equation, we'll have this origin symmetry. When we replace y with negative y, and at the same time x with negative x, we get the same equation. So that's the test for our origin symmetry. We can see this here. So through the origin, it's symmetric. So if we take this point here, this distance here is the same as this one here. So it's symmetric across the origin. You can kind of think of this one as first you reflect across the y-axis, and then you'll reflect across the x-axis. And if it falls on to the same line, it has origin symmetry. Okay, so example 1, we want to determine the symmetries of the graph of the equation x minus y squared equals y to the 6th. So by just looking at this, we see that y is raised to even powers, x is raised to an odd power, so they're not raised to the same parity, but rather they're raised to different parities. One is odd, one is even. And the one where y is to an even power, x has no restriction, that is the x-axis symmetry. So we should get x-axis symmetry for this one. To do this algebraically, we replace y with negative y, so x minus negative y squared equals negative y to the 6th. when we raise a negative to an even power, we get the same thing but positive. So this is just y squared, and this is y to the 6th. And we get the same exact equation, so it does have the x-axis symmetry. So I'll say it is symmetric across the x-axis. If we wanted to test the y-axis symmetry, we replace x with negative x. And we end up not getting the same equation. So this is a different equation since this is negative here. And that means that we don't have symmetry across the y-axis. So we'll say no. No symmetry across the y-axis. And then for origin, we do both of those at the same time. Negative x minus negative y squared equals negative y to the 6th power. Similar thing happens, we get negative x here minus y squared. That equals y to the 6th. And we get the same equation that we had right here, which is not the same as the original. And because of this, there's no symmetry through the origin. That one just has x-axis symmetry. Again, we can just look at the equation. Notice that y is to the 2nd power and the 6th power, both even powers. And because of that, we can already kind of know that there's x-axis symmetry. Example 2, determine the symmetries of the graph of the equation. We have y equals x cubed minus 2. One thing to remember is that there's kind of an invisible 1 here, but we can write this invisible 1 in a different way. We can write it as x to the 0th power, which is an even power of x. This one has both an even power of x and an odd power of x. When this occurs, we really won't have any symmetry for this one. Another way to see this is to actually graph this equation and just look at it and see that it has no symmetry. So I'll go to Desmos for this one. We could do this in our normal graphing calculators as well, but I'm using this one because it's just a little bit easier. Y equals x cubed minus 2. This minus 2 is shifting it down 2, and because of that, if we would look across the y-axis, it's not symmetric. If you look through the origin, it's also not symmetric. Across the x-axis, it's not symmetric as well, so this one has no symmetries. This one has absolutely no symmetries. So no symmetries for this one. You could go through the algebra for each one, and you'll see each time that you get an equation that is different. Okay, for example 3, determine the symmetries of the graph of the equation. We have y to the third power equals x minus x cubed. There's an invisible one here, an implied one. So x is all to an odd power. Y is to an odd power. And if we go up to the chart up here, the situation we're in is right here. Both of them are to odd powers. And because of that, we can just say that this has origin symmetry. So I'll say this has origin symmetry. Algebraically, what happens, you have negative y to the third power. When you raise a negative to an odd power, it gives you the same negative answer. And when we do this on both sides, we'll get a negative 1 on both sides, which we can then divide by and get back the original equation. So this is negative y cubed equals negative x minus negative x cubed. I'll rewrite this one time. This is negative x plus x cubed. If you negate everything or divide everything by negative 1, this gives you y cubed equals x minus x cubed, and we get back the same original equation. So those two are equal, which means we have that origin symmetry. We can also verify our answer by looking at the graph of the equation. So we have y cubed equals x minus x cubed. And this one looks pretty funky, but it is symmetric across the origin. If we would fold this over and then fold it over again, it would fall right on top of itself. So this is symmetric through the origin.